Hello, everyone, and thank you for joining us today. Welcome to Megger's Testing Tactics webinar series. Today's topic is Advanced Testing and Assessment of Instrument Transformers. My name is Michael Fleischer, and I'm the Digital Marketing Specialist for Megger. I'll be acting as the moderator for today's presentation and supporting you on any technical issues or questions for our presenter. On the right side of your screen, you will see a control panel that looks similar to this one. You can submit questions at any time during the presentation by typing in the box highlighted in red, and I will read the questions out at the end of the webinar. Additionally, certificates of attendance, copy of the presentation, and link to the recording of this webinar will be sent to all attendees in 2 business days. Our presenter today is Volney Naranjo, Senior Applications Engineer. Also, to assist with the question and answer session, we'll have joining us Abel Gonzalez, Senior Applications Engineer, and Daniel Carreño, Applications Engineer. All right, let's go ahead and get started. Thanks for joining us today, Volney.
Thank you very much, Michael, and welcome everybody to this monthly Testing Tactics webinar. Today, we're talking about instrument transformer testing and especially the assessment of the results. So we have this agenda. We're going to talk about the instrument transformer standards. We're touch briefly on how the testing instruments have evolved, and of course we're going to focus on the test results and the assessment, and then we will have the Q&A session. So we have a kind of a very small agenda, but it's packed of information. So let's look into this. As a background, why to talk about this? Well, instrument transformers are critical for power systems. They are the ones that bring primary signals into the metering and control devices as secondary signals. So you will get voltage, secondary voltage, and secondary current for the system to be controlled and protected. So they are a linking device or linking instrument or apparatus, and whatever condition they are is very critical for the power system. So any maintenance program, it's fundamental to have in place maintenance procedures for these instrument transformers, and especially to verify that they're in proper condition, and furthermore that they are definitely performing under correct status or correct conditions, and that they are going to represent the primary side accurately. And so for this purpose, you want to have a maintenance program that helps you to determine different instrument transformer parameters, and that then you can use to evaluate the condition and the performance from this according to the standards. And so it's not only about getting results, it's about evaluating these results according to the expected performance of the instrument. And in this, it's kind of a little bit different from other testing that you do. For example, on circuit breakers, you get your results and you compare to manufacturer values. But in instrument transformers, you have to do some assessment. You have to perform some calculations with those results from the test, and then evaluate that as against certain limits that are established by the standard. So there are several characteristic assessments, and well, we are focusing mainly on one here. And throughout the presentation, I'm going to be talking mainly about CTs, but of course these concepts apply also to VTs, voltage transformers. Then well, this assessment needs, as I was mentioning, results from all the testing, but then it needs some calculations. And well, these assessments were not common when you tested instrument transformers, because performing that assessment required these calculations that was not easy in the field, or you didn't have all the test results because the instrumentation that was out there was not to the level to be able to get all the results and to get all the accuracy and be capable to perform everything. Of course, we have technology now, and test instruments have evolved, so now you can get these assessments performed right away on the spot uh, when you finish a test. So the advanced testing and the assessment implies determining a comprehensive set of parameters from testing, from the testing of the instrument transformer, and then evaluate and assess if that instrument transformer is in performing as designed. So that's what we are going to look into, the different standards and the different testing techniques and how have they evolved, and then we're going to evaluate how they we're going to look into results, a couple of results. I don't think we have time for to cover everything that is related to these, but at least we are presenting the concept and the and a specific look into one of the results. So um, the standard. So, well, we are in the US. We cover mainly, or we follow mainly the IEEE standard. So the ANSI IEEE standards. And for instrument transformers, we have C57.13 series. It's a series of documents with a main document being C5713, which it's the standard requirements for instrument transformers. So it covers both. It covers current and voltage transformers. And well, it has the electrical and dimensional mechanical characteristics, and also talks about safety. But very important for our topic today is that it defines the accuracy classes for metering and relaying circuits. So the accuracy classes is kind of what we are focusing today. We are verifying that the instrument can perform as per that classification that was designed to. And well, the standard or the document also establishes all the measurement and calculations for all the different tests that need to be performed to assess that transformer. And some of these tests that are here are mainly for factory purposes or for type testing or routine testing, but there are also tests that apply for field testing. And those are basically ratio and phase angle, demagnetization, impedance and excitation measurements, polarity of the terminals, resistance measurements. And those are the ones that we are going to be talking about in this test, in this presentation. As an additional resource or information source, source of information, we have C5713.1, which is the guide for field testing of relay current transformers. So this is the document that specifies more details about relaying class current transformers. It adds to the field test methods, and it also shows the methods to evaluate if the instrument transformer is performing as designed. There are other documents that do not relate to our topic today, like C5713.2, which is conformance test procedure, and also C5713.3, guide for grounding of instrument transformer, secondary circuits and cases. And this is mainly about safety. There's one that concerns to the topic C5713.5, which is the standard for performance and test requirements for instrument transformers of 115 kilovolts and above. This covers mainly potential transformers, voltage transformers, and then the accuracy classes that were defined in C5713. Well, was kind of a document that brings these accuracy classes from a long time ago. And well, now we have electronic meters, and we have smaller versions that connect to these CTs. and we need higher accuracy requirements. So these standard define new metering accuracy classes, also new burdens, and also new test methods. So this is also a very important standard reference document for this topic. So you're going to receive this presentation, you're going to have this video available, so you always can come back to this presentation and look for these references as a quick guide of what to look at. So let's look into the accuracy classes definition, and especially for metering. I have both metering and protection. So first we're talking about metering, and so what is the accuracy class? Accuracy class is basically when it defines for CTs and BTs operational limits. So it tells us the ratio correction factor and the power factor limits, and specifically the power factor is defined that it has to be between 0.6 and 1, or its corresponding phase deviation in degrees, and how the ratio correction factor defines a minimum and a maximum for that ratio correction factor. So every transformer has a transformer ratio, and you can define the ratio correction factor from that error, creating a minimum and a maximum deviation in magnitude, and also we already have defined the maximum deviation in phase. So and the other thing to consider about the accuracy class is that this applies, or the manufacturer guarantees that the instrument transformer will perform within these limits if there's a specific burden, or there's a burden that do not exceed certain rating, and if some loading conditions are present. So let's look at the table. We have a metering accuracy class definition here. We have 0.5, 0.15 as 0.15, 0.15, and 0.3. So this is basically telling us the error magnitude, how big the error can be in the transformation of our primary signal. And of course, this is on the positive side and the negative side. So we have a minimum and a maximum, and we have that for voltage transformers and current transformers. And we also see that this is specified for specific load conditions. So these voltage transformers will perform within these limits if the voltage is between 90% and 110% of the rated voltage. We're talking about metering class. So metering class, really, you're not interested in metering if the voltage is below 90%, which will be like a fault condition. The opposite happens on current transformers. Current transformers, they need to perform at 100% of rated current, and if you have no load, or the load is too small, then probably you don't need such a high accuracy. However, with how the power systems operate now, you would have times during the day that you will have a full load, or you would have a reduced load. So these transformers need to perform also down to certain levels. And that's why here we need to go down to 10%, different from voltage transformers. And again, you have the limits, the minimum and the maximum limit for the ratio error, for the ratio correction factor. Now, this is in relation to the construction of the CT, and this is what the manufacturer guarantees, but this also depends on what is connected to that instrument transformer. So this instrument transformer, they do not deliver power, but they definitely have a load connected to them. They have a circuit that is basically composed of the wiring and the metering and control devices. So you have relays, you have coils, you have meters connected to these transformer, and well, it is providing signals, voltage or current, but of course it needs to provide some power to these elements. So the loading conditions must not exceed certain limits. So right now we're focusing on the burden, sorry, on the accuracy class, and later on we'll talk about burden. So to kind of and get more or go a little bit more in detail about these accuracy class and these limits, let's talk about the current transformer equivalent circuit and see how or where these limits come from. So here we have the equivalent circuit. We have our primary side and then the secondary side with the excitation branch, and this is representing the secondary winding resistance. We have our terminals, and this is the external burden that is connected to this transformer. This is the load that this instrument transformer is feeding. So in ideal conditions, hold on. So in ideal conditions, we have that there's no losses, and then whatever primary current that we have represented in terms of the secondary side using the number of turns should be represented as secondary current without any deviation. So it will be the same, a proportional magnitude, and it will be with no phase deviation. They will be in perfect phase, in perfect alignment from one side to the other. Now, there are no ideal CTs or voltage transformers. I'm talking about here a current transformer, but this same concept apply for voltage transformers. So there are no real ideal instrument transformers, so you have some losses. And what those losses cause is that your magnitude on the secondary side is going to be deviated from the proportional current on the primary side in the magnitude, and then you're also going to have a phase deviation. So if you think about the ratio correction factor having a minimum or a maximum, and you think about the power factor limits defined by the class, that means that you are going to have a magnitude that is going to be less or higher than what the proportional primary current is. So that's where you get your maximum and minimum ratio correction factor. And then for the phase deviation, we know that the limit is between 0.6 and 1 power factor. So the corresponding, that is the corresponding cosine of this angle. So in this case means that you may have a deviation that it's lagging more or lagging less, because we are always in the lagging side, at least for this case. So that defines your four limits. So if you think of those four limits, two maximums and two minimums, and you bring that into the coordinate plane, you can draw a parallelogram. So in this case, we have for 100% of rated current, we have minimum ratio correction factor and minimum phase angle. Then we have another corner of this parallelogram defined by a minimum ratio correction factor and maximum phase deviation. And the same thing applies for the other two vertices. So you have maximum ratio correction factor with minimum phase deviation, and maximum correction factor, ratio correction factor with maximum phase deviation. So those limits defined by the accuracy classes define this parallelogram, which is part of what an assessment of the performance of a CT or a voltage transformer for metering purposes need to include. So it's not only about getting the ratio, it's about getting the assessment of that ratio in relation to this coordinate plane according to the accuracy class. And in this graph, we can see that it covers the 100% of rated current and 10% of rated current. And it shows or summarizes most of those accuracy classes. I guess for purposes of the presentation, I'm not showing all of the parallelograms. They are in the standard. These are taken from IEEE C57, but I guess the concept is what we are interested in understanding. This is something that when you see a report from a CT or a VT, and now you see all of these graphs and information additional to the test report, that's what we are trying to address or to show here, that what is being done. A little bit more on the accuracy classes. This is another way to see or to understand the concept. In this case, we are saying that the standard class 0.3, this means that the transformer will guarantee, or the manufacturer guarantees 0.3% from 100% and above up to the rating factor of the transformer, and below 100%, it will guarantee half of that accuracy, 0.6%. And this only happens down to 10% of the voltage or the load. If in this case is for current transformers, so the load. If the load goes lower than this, the accuracy is not guaranteed. So the CT is not going to perform under those conditions or perform well. Then you can see how the 0.15 extends the accuracy range down to 5%, but still it's still half of the accuracy when you have 100% of the load. Now, the new accuracies that were defined by C57 13.6 are the high accuracies instrument transformers. So now the manufacturer is guaranteeing this accuracy of 0.15 down to 5%. So throughout the entire range of operation, and there's one more accuracy class that guarantees even down to a lower loading condition. So of course, the higher accuracy and the bigger the range, you have a more expensive CT or a voltage transformer, and of course they need to be installed in the proper application. So they might not be, you might not be interchanging these type of classes because you may not cover your application accurately. Okay, I hope that makes sense. And now let's talk about the other part of the accuracy class classification. So now we need to talk about the burden. So this circuit, I'm showing a different circuit here, but it's a different drawing, but it's the same circuit. This is the CT or the V, we can have the same thing for a current voltage transformer, but this will produce a voltage or a current at these terminals, and now this burden cannot exceed certain limits, because if not, this is not going to perform as specified. So that's what we also have from the standard. We need to guarantee that the burden that is connected to this instrument transformer is not exceeding these limits. So we have the designation. So in IEEE world, you design the burden. The designation for the burden it starts with a V, and then it shows the maximum impedance that can be connected to that circuit. If we look at the impedance, total impedance, it's 1.8 and corresponds to this rating here. But it is made out of a resistance and an inductance. So you can also have that measure that information, determine that information. And this burden is also expressed as VAs. So you can have maximum VA of 45, or this is telling you that this instrument transformer can only supply a load up to 45 VAs if you are using 5 amps circuit secondary current transformers, in this case CTs, and um, 1.8 if you are using a 1 amp as a secondary current. And the burden can also have a maximum power factor or a specific power factor. For metering purposes, you have 0.9. For electronic burdens, is 1. So you can see here that CTs designed for electronic burdens can handle just smaller loads and not as big as the metering burden. So this is what the instrument transformer can handle, and that's the maximum configure, the maximum characteristic of this load to be connected. So very important in the testing process to test this burden, to get this value, to get the actual value, and use that value for the assessment. Once you get all the values from the CT, once you get all of these parameters, resistance, excitation characteristic, turns ratio, you need to assess and you need to simulate how these CT will behave with this load. And well, it can happen that the load is so basically two things can defeat the operation or the performance of the CT. You are exceeding the load, or something is going it's happening inside the CT that it's affecting the output, and then it cannot supply the load even though it is within the limits. So that is also what the assessment is about. And we can see that this burden definitely affects the excitation or the performance of the instrument transformer. We can see that the excitation current, it's dependent on the burden that it's connected to its terminals. So very, very important to measure and to use it for the assessment. So all what I've been showing is for instrument for current transformers and relay metering purposes. And now this shows for protection purposes, for relaying purposes. So here the classification, it starts with a T or with a C, and it will have a number next to it, like 400, 800, 200, and that is basically relating to the burden that it can handle. So a C800 can handle a burden up to 8 ohms of impedance, and so on. Then these are the limits for the ratio error. So we were talking before in metering classes at accuracies of 0.3, 0.15. And because we need to accurately measure how much power is being delivered, and this translates into dollars. In this case, we are not so concerned in the relaying side. We are not so concerned about the accuracy. We just need the instrument, the transformer, the instrument transformer, not to saturate and reflect to a certain degree the condition of the primary side. So now we have limits of 3% at rated current and 10% at 20 times the rated current. So this is a fault condition. And when you are talking about kiloamps, when you are under rated current of the hundreds, really you don't care about the 1 or 200 amps there. So really that the accuracy doesn't need to be that high. And well, there's one additional classification, the X, which this one needs to be defined by the user. These are special application CTs, and I think they're used for transient conditions and all of that. So, and we have the same table for burdens here, and there are some CTs that are referred they're not covered in IC, sorry, IEEE standard, but they are covered, and IEEE standard refers them to IEC 61869-2, which is the corresponding family of standards in the IEC world. And this is the reason you would need to sometimes here in the US test CTs under IEC standards. So that's a quick reference about it. And not to go into many details, but these are the tables from these cities for these cities from the IEC standard for these cities for transient performance. So there are three classes, and they have a kind of a high accuracy, 0.5 1% compared to regular protection CTs. They can also have, you can see here also the phase deviation, the maximum allowed phase deviation. And these CTs are built for transient conditions. So they have other parameters, other characteristics that need to be evaluated, that need to be assessed, like the rated value of the transient dimension and factor KTD, the rated value of the secondary loop time constant TS, or rated resistive burden. So you look specifically at the resistive burden, not at the DC characteristic of the burden, not the inductive part. And well, these are parameters that need to be calculated from the results and then compared to the characteristics of the CT. So these when you test these type of CTs, you also need to calculate, or the software needs to calculate these values. So that's part of the assessment in these instrument transformers. Okay. So having covered that aspect of the standards and having shown the details about the accuracy classes and the performance requirements, as a transition, let's look into instrument transformer testing evolution. So as I was mentioning, the test requires kind of a comprehensive set of tests, and previously, years ago, you would have discrete instruments, separate instruments for each of the tests that you need to perform. And of course, you will get separate results, separate reports that won't help you to do the assessment quickly and easily. Technology evolves, and then we got multifunction test sets, meaning that you have several tests that can be performed from one single box, and but still you need to do the testing of each tab of the current transformer or the voltage transformer like separately. So you need to repeat that multifunction run on each tab. And then the concurrent function was added to the test sets. That means that at every test, it will test for all the tabs at the same time. And of course, this expedites how the timing and the efficiency of the test. And now, because you have all of the tests in these multifunction instruments and concurrent instruments, added more tests to all the set of activities that you can perform with this instrument. So now you have a comprehensive result in one single place, and the software can use that information to perform the calculations that are needed to perform the assessment. So more details about the discrete, multifunction, and concurrent. Of course, I already mentioned for discrete instruments, you get individual test reports. Sometimes these instruments will not have the accuracy requirements to be able to test a 0.15 class accuracy class instrument transformer. So you need very accurate instruments now if you're testing this type of metering CTs or VTs. And performing individual tests is inefficient. You can spend 1 hour testing one CT for all the taps easily because you need to change leads, you need to swap instruments and open different software. So it's inefficient. And well, when you go to test CTs or VTs, you only don't have one. You have many of them, and it will take a lot of time testing CT. So it's important to consider an instrument or a tool that can help you expedite the testing. And even if you do it with discrete instrument, then if you want to run the assessments, you will need to run manual calculations using those results from the tests. Multifunction instruments, they give you good efficiency, but may not cover all of the tests. So if it's one of the early generation of multifunction instruments, you may not have all the tests that are needed. They do not perform the test concurrently. They just do tab by tab. And yes, you get an integrated report, but again, you may not have all the tests, or you can still have the accuracy limitation. So they might not be suitable for metering class CTs or VTs. And because you don't have everything there, you cannot perform the automatic assessment. Uh, with the concurrent, you have everything there. You have multifunction, you have all the tabs at the same time. Of course, these streamlines your efficiency. You can test CTs in less than 10 minutes. Once you connect to them, you get the required accuracy. And you can test not with one single instrument, you can test different type of instrument transformers. So there's not an instrument for VTs, there's not an instrument for CTs. You can get an instrument that can do all of them, and even capacity voltage transformers that are also kind of an additional, or it has its own complications. So you can test all the instrument transformers with one single instrument, and everything is in one single place, so it can perform the assessment. Let's look into the results. Let's talk about the different test activities that you perform. So of course, any electrical equipment, the very first test you want to run is insulation. And you want to assess the insulation. And in this particular case, I'm showing insulation resistance. But depending the type of CT or VT, the voltage level, the current level, you may have oil insulation, or paper, cellulose immersed insulation. You can have also resins. So you have different insulations that sometimes just a simple insulation resistance at 500 or 1 kilovolt may not be enough. You need to consider other insulation assessment tools. But anyhow, the insulation resistance, it's a very quick test that allows you to determine if at least there's a transformer still alive. The insulation is the life of any transformer. So if there are insulation problems, there's no point on trying to test the other elements there, the other parameters, because there's no actual functional transformer there. So this is not used for any assessment, but it's really important in the process of testing. Then it comes winding resistance. So we're talking about determining this parameter here, the resistance, the DC resistance of the secondary side of the transformer. And of course, this is very important for the performance. If this resistance increases from the original value, then you're going to have a voltage drop after these at these terminals. Whatever induced voltage is not going to be reflected as the output voltage or current or whatever signal you're trying to get from this instrument transformer. So it's very important to get this value. There's the way to get this value is through applying DC current through the terminal. So we are circulating DC current through the terminals of the instrument transformers, secondary side, and also at the same terminals we are measuring the voltage drop. So with current and voltage drop, we can calculate resistance, and in the process, this current, DC current that is circulating through the winding is saturating, is magnetizing this branch. The core is being magnetized, and well, if that branch or that core remains in that condition, it will affect the performance of the transformer for the other tests, or for the actual operation of the CT. When you energize, it will probably create inverse current that will cause a trip. So you need to demagnetize the instrument transformer when you after you run a winding resistance. And this doesn't give you an actual result that you can use for the performance assessment, but it can be measured. You can measure the remanence, and it can be indicated there that you in the report that the CT or the VT was demagnetized and it's in proper condition. It's demagnetizing properly. After you have the CT or the instrument transformer demagnetized, you can perform the excitation test. And the purpose of the excitation test is to, of course, understand the condition of this section of the instrument transformer, of the core and the magnetizing, the inductive part of the transformer. The test consists of applying AC voltage through the secondary terminals, and as this voltage is increased, we are measuring the excitation current, how the current that needs to circulate or that will circulate through this branch due to the voltage that is being applied. And the terminals on the primary side need to be open for this test. This will show a linear behavior to a certain point. So as you increase voltage, current will increase proportionally, linearly through a good amount of the test. And at certain point, this circuit will not be able to handle more current. Will not be able to handle more flux. So it will saturate, and then it's not going to continue, or it's not going to continue representing the ratio accurately. So at that point, the instrument transformer loses accuracy. The ratio correction factor gets out of the limits. So that characteristic is gathered through these tests. And that point where it starts saturating, it's called the knee point, and from that point on, the current will increase very fast, very rapidly as you increase the voltage. So around every 10% of voltage increase will increase 50% the current to a point that it will be linear, again saturated, and won't increase anymore. I have results that I'm going to show on this. So then the other part that you want to verify or get results from is this ratio. So the number of turns on the primary side in relation to the number of turns on the secondary side. So, and as we already saw in the vector diagram previously, you're going to have a ratio error there. So it's not going to be exactly as the number of turns. And then you're going to have a phase deviation, so it's going to be affected also in phase. So with this, now you can see that we have pretty much all the parameters here in this circuit. So in essence, we can model the instrument transformer, and we can perform calculations from that point on. Polarity is also checked because you want to verify that if, depending how you need the instrument the instrument transformer to operate, if you're injecting current on this terminal, you want current to go out on this terminal. So that is the polarity verification. And this is for purposes of the protection system, how you want currents to go into the protection or metering devices. So, and you want to reflect the same direction as the primary current, so that if the terminals are reversed, that you can detect that with the polarity test. And well, finally, the burden. Remember, this is not a test on the actual CT. At this point, well, for the testing of the instrument transformer, you disconnect the burden, the circuit that is connected to it, and you now, once you finish testing the CT or the voltage transformer, now you go and connect the instrument to this circuit and measure this impedance, this total impedance that you see from the wiring that goes from the control cabinet down to the individual elements. Okay, so let's see an actual test result. So here we have a current transformer that is a metering class, 0.3 accuracy class with a burden up to 1.8. And well, if we remember the table, that represents a maximum VA of 45 VAs. So this is the nameplate of the transformer. We are evaluating this and under the ANSI standard. This could be, depending this accuracy class, you could have IC standard. So remember, there are different standard. Each instrument transformer will have its own classification, and depending what standard it was built to, you also need to evaluate against that standard. And that was my reference to the transient transformer. So if you have a transient transformer, you need to select IC for the assessment. This is what determines how this information is going to be used for the calculations of the assessment. So everything what we see here is results from a test on this CT. You can see that it is a multi-tab CT. You have all the ratios here, and well, it has across the entire winding, X1 to X5 is a ratio of 4,000 to 5. The measured ratio is 3,999.47. So that means that there's an error of 0.013. So according to this accuracy class, we could have plus or minus 0.3% here, which we are far from that. So meaning that the ratio is very good. And we can start picturing this in a parallelogram, and we know that it's going to be pretty much in the center of that parallelogram, at least in what relates to the y-axis. Oops, sorry, I pressed the wrong one. So continuing with this, well, this is just information about the testing conditions, how this ratio, this measured ratio was obtained, the voltage and the current that was circulating when running the test, and the induced voltage on the primary side. Then this is the knee point. Well, this is integrating all the results. So this is a result that it's taking from the saturation curve, from the excitation curve, and we can see that this instrument transformer had a linear behavior up to 267 volts and 0.0353 amps. From that moment on, the ratio was not anymore linear, and that's where the CT kind of starts deviating from the expected performance. In relation to the ratio, we have the phase deviation. So 359, 360 degrees, meaning 0 degrees. There's no deviation or very little deviation in phase from the primary side. And the polarity was correct for all of the terminals. And we also have the resistance for each of the taps, and the entire winding resistance is 2.020 ohms. In relation to this resistance, it is important to have that corrected to a reference temperature, so you can always compare results. Resistance is temperature dependent, and if you do not correct and don't show that there, you might be comparing two values that are not at the same temperature. So always be aware of the temperature of the test and or the instrument when you run the test. And then down here, I have the table that shows the burden. So this is the actual VAs that were measured. This is the actual rating or burden that is connected to the CT, that circuit that goes from the terminals down to the instruments, to the control or metering instruments. It's a 2.59 VAs with a power factor of 0.63 or an angle of 308 degrees. So these are results, and this is what we were used to get from an instrument transformer tester. Now, from this point on is the assessment. You are using all of this information to evaluate against the standards. Well, this is part of the excitation current, and here we are showing the excitation curve for all of the combinations of the tabs, being this pink one, the one corresponding to X1, X5. And this is the entire winding. Here we have the knee point, which is where the curve starts saturating, and then you can see that the voltage will not increase anymore, and current will be going to the maximum. The saturation test is performed up to 1 amp to avoid damage, because we are doing it from the secondary side. And part of the assessment is to evaluate the conditions of the instrument transformer under fault conditions like 100, 50%, 200%, 20 times or 200% of the rated current. And of course, we are not doing that in field testing. So with the use of software, this can be extrapolated and it can be determined how it will behave at higher currents. You can extrapolate the curve, and using all the other parameters from the instrument transformer, from the measurements, you can perform the assessment. So this is one of the assessments. Now, in this table, we can see the ratio error at different rated currents for different loading conditions. So this is the real part of the ratio, and it is looking at the magnitude, how the magnitude will be affected of that as the load increases. So at 200%, at 100%, and in the case that you have a load or a burden of 45 VA connected to those terminals. So all of these are situations with different loading conditions. And if we remember burden result, I brought it here as well, 2.59, we can see that actual burden is being used to evaluate the instrument transformer. So the purpose is, as we saw from one of the graphics before, the idea is that the rating or the class or the performance of the instrument transformer remains constant, remains linear or identical throughout a range. And that's what we can see with the table, or the graphical representation of this table in these curves here. So this curve here, the blue curve, is at 45 VA. And well, you have from 1% of rated current up to 200% of rated current. So yeah, it's not totally linear, but you can see that it kind of shows a linear behavior, and especially at the areas where the instrument transformer needs to perform better, it has a more linearity. So this is the part of the ratio error. Now remember that we also have to evaluate the phase deviation. It's not only the ratio; it's also the phase deviation that you need to assess and to evaluate. So the we have exactly the same thing at different conditions of current, of rated current, and different loading conditions. And this is with the actual burden that is connected at that CT that moment. So you are not only simulating different loading conditions, but you are evaluating how it will behave with that specific burden. So if you add any element to the system, to the protection system, you want to retest that burden, and well, probably you are retesting also the CT, you are getting new parameters and you are simulating that. So this is a way to verify if your added device is going to affect or not the behavior of your CT or your VT. And of course, designers will do the calculations, but that's what you need to verify in the field once it is installed and before going into operation or for maintenance purposes. So as I said, there's a lot of information, and you can go into many details. And also this, I've been talking about VTs or CTs indistinctly. In a little bit of details about VTs before we end the presentation. We are 5 minutes into the hour. So before the hour. So and in VTs, we do pretty much the same type of test. We perform the insulation assessment, and remember, it's important to consider additional insulation assessment if you have a certain type of instrument transformer that has a more complex insulation system. You perform winding resistance, demagnetization, saturation as well. This is not a common test, and this is probably part of the advanced test that you need to perform. In VTs, the typical test that you will run will be the ratio and the winding resistance, but saturation and a secondary short circuit impedance were not that common. But these two tests are required for the full assessment of the conditions of the system. And then you have the phase deviation, the ratio and the phase deviation, as well as the polarity, same as before. And with all of these sets of results, you get the same type of situation. You get your results in a table, and then you perform assessment. Now, because we have a metering CT here, a VT, sorry, I think I didn't show the parallelogram for the other one. I don't know what happened with that slide, but well, I'm showing the parallelogram here for this VT, and we are showing where the result, this error and this phase deviation falls in. And well, it's well within the parallelogram. It's not exactly in the center, but it's inside the parallelogram, and that's what the assessment is about. If it is there, it means that my instrument transformer is going to perform properly, or it's performing properly. And then this information from the excitation test, from the parallelogram, from the short circuit impedance is also used to run the evaluation across different ratios, different loading conditions and different burden conditions. In this case, whoever ran this test did not measure the impedance on the circuit, the circuit connected to the CT. So we don't have the actual evaluation at real conditions, at real burden, but still you can see how linear it is, the behavior throughout the range of the instrument transformer. A couple of details about CVTs. CVTs are basically a combination of an inductive part, like any regular VT, but then you have a capacitive section that helps in reducing the voltage and help in the ratio of these CT. So making these type of CVTs, these voltage transformers, more economical and practical to build. So the ratio in these instrument transformers it's a little bit tricky to measure, because now you are dealing with the capacitive part. You need high voltage to perform the test. At least you need 2000 volts and a very accurate metering system inside the instrument to be able to get the proper ratio and the proper phase deviation. Other than that, you also need to measure the capacitance. You need to determine the capacitance, the condition of each of these capacitors, and the overall capacitance, and of course the power factor on this capacitive section. And this can be tricky. There's a combination of switches, of grounding switches here, that you need to understand the condition, or you need to understand the constructive part of the instrument transformer to be able to operate properly those switches and test each individual capacitor or each side accurately. So it adds a little bit of complication to the test, and you need probably to use an instrument that it at least has a good voltage to excite these capacitance and generate induced voltage here. And then once you get the results, you can do the assessment, which applies very similar to what we discussed. So to finalize, the assessment is a calculation and evaluation of the instrument transformer performance characteristics as per the standards. It is class dependent, and you need detailed nameplate information. You need to provide accurate information to the instrument or the software for it to be able to evaluate against the standard properly. And then you need comprehensive testing. You need to run all the tests that are recommended in the standard to be able to model that circuit, that instrument transformer circuit, and also use the information from the actual burden to be able to assess and simulate the performance of the instrument transformer. Of course, we have instruments that can do all of these tests. We have the MRCT, which is an instrument that has as a patent method of simultaneous testing, the concurrent method. And well, you reduce the time of testing drastically. And it's also an instrument that can perform tests on all type of instrument transformers, CTs, VTs, and CVTs as well. And it has metering accuracy, with also the possibility to test relays with this instrument. So you're testing an instrument transformer, but really that makes part of the protection system. So you may need to work on the relay side as well, and this provides a means to test an instrument, a single phase relay. And as I mentioned before, you can measure the burden as well with this instrument. And the MVCT is a lighter instrument that uses a different technique for the saturation. There are some CTs that require or will saturate, will have that knee point at 30 kilovolts or 15 kilovolts, and then you will need higher voltages to test that. or you can use an alternate method to saturate. Instead of applying AC voltage, you apply AC current and measure the saturation through that system. We have presentations that talk about that method. It's a lighter instrument because now you don't have a transformer that goes up to 2 kilovolts, and it provides the same features as the MRCT, with the only exception that you cannot test CVTs with this one. You have to use higher voltage for CVTs, and so this instrument won't apply, but you can still test the insulation resistance. You can also test burden and do all the other tests, and it will perform the same assessment on all of the instrument transformers that it can test. With this, I'm done with my presentation, and I went 5 minutes after the hour. Hope that was valuable for you, and we're ready to go into the questions. Michael.
Wonderful. All right, thanks, Volney. So, as stated before, the presentation portion of our webinar has concluded. We're going to take some time to answer as many of your questions as possible. If you have any questions, please submit them now into the Q&A box on the GoToWebinar control panel. For those of you that are leaving, when you close the webinar window, a survey should pop up on your screen. We would greatly appreciate it if you could take a couple of minutes to provide your feedback so we can continue to improve upon our future webinars. On the survey, there's a field where you can also request a quote or a demo on any Megger products. A copy of the presentation, certificate of attendance, and a link to the video recording of the webinar will be emailed to everyone in about 2 business days. You can also view video recordings of previous webinars, as well as register for our upcoming webinars on our website at us.megger.com/webinars, and register for our next webinar on Wednesday, March 24th, titled Advancements in Primary Current Injection for LV Current Circuit Breaker Testing. So let's jump into your questions. Our first one I'm going to direct over to Abel Gonzalez. Abel, is power factor related to the burden, not the primary measured load?
Hi, Mike. Just to confirm, you can hear me?
I can.
Okay, thanks, Mike. So yeah, that's an interesting question, because in this case, what we are talking about is about the measurement of the burden of the CT, which is essentially the impedance connected on the secondary of the CT. So the power factor that we were talking about in this case is the power factor of the impedance connected on the secondary of the CT, not the power factor of the load that the CT is trying to measure. Okay, so in this case, we're talking about the power factor of the load connected to the secondary of the CT, which is the burden connected to the secondary of the CT. Okay, in other cases, we would be talking about the power factor of the load connecting to the system. The term is the same. It has the same meaning. It's just that in this case, it's aimed at telling us what is the ratio of resistance versus reactance that we have connected to the secondary of the CT only. Okay, that's the load that we are considering in this case.
Thanks, Abel. Our next question is going to go over to Daniel Carreño. Daniel, what are the common causes of high voltage instrument potential transformer failure?
Thank you, Mike, and hello to everybody in the audience. Well, if we want to look or go back to the causes, I think it's a good practice or a good idea to look at the stresses which our transformers, when they are in service, will be under, right? As the moment we energize the transformer, of course, we'll be having the electrical stresses, right, because of the different potentials between the different parts of our system. When we have a current flowing, that will increase the temperatures. That will be a thermal stress, mainly for the insulation. And we also have, external factors like environmental or chemical. For example, if we have an oil field unit, and if that oil starts to degrade, those byproducts can attack the insulation of the system, mechanical stresses in the case of failures like short circuit. So those will be, again, of course, causing the issues in my transformer. And I guess we can directly correlate those to the tests that we perform to do preventive maintenance or even discovery and investigation of any problem.
Thanks, Daniel. Over to Abel. Abel, what do we do in the case of a high impedance relay, such as an SEL 587Z, in regards to the burden?
Okay, that's a very interesting question. The thing with high impedance relays like the 587Z is that they themselves have a very high impedance in the current inputs. For example, the 587 itself has 2 kilo ohms in the current inputs, and that's what makes it a high impedance, differential relay. Now, the thing is that those are used to measure, or what the current that's used as input to those relays is actually the difference between the currents, or at the summation point of all the CTs connected in typically a bus differential scheme. In that case, the thing is that the current that the relay is actually measuring is not the current connected to the secondary of any individual current transformer, but the current that results from the sum of all, or the difference between the currents of all of the transformers connected together. So if at the summation point the currents going in equal the currents going out, there's no current going through the relay. The point here is that for that case, you would test each of the current transformers individually without considering the impedance of the relay. Actually, one of the most popular current transformers used for this type of scheme is the class PX current transformer. And when we go into a specification of those current transformers, one of the things that we use to specify them is the resistance connected in the secondary of the transformer without considering the differential part of the circuit. So the answer is you test the transformer's load as if there were no differential part, because you know what the resistance on the differential part is going to be, and it's going to be dominated by the resistance of the current inputs of that relay that you are connected, because that's 2 kilo ohms, and then you have an MOV there and things like that. So the answer is test the relay as if there were no differential. I'm sorry, test the current transformers. There were no differential. Test them all individually to know exactly what the situation is for each of them, because at the summation point to the relay, it's only going to go the difference in current between each of the, and a very small amount of current will make that relay operate. Okay.
All right. Our next question is over to Daniel. Daniel, if we measure the transformation ratio of the CT by voltage, what would be the maximum errors allowed by the standard deviation?
Thanks, Mike. A great question. We get that question a lot, and I guess it comes from the fact that when we think, if we have a current transformer, then I guess common sense dictates that we have to use a current method, right? A primary current injection method to test the transformation ratio. But if we look at the modeling of the CT, right, we will see that it's just a transformer with the secondary side short circuited. So the principle of operation doesn't change, the physics don't change. So we can use our voltage method to test that CT ratio, and we don't have to have any special consideration or correction factor for the results. So what I'm going is for the analysis, right? We use the exact same limits that we get from the standards. There is no change in terms of the accuracy if you use one method or the other. So again, you can use the same criteria to analyze the results, either by the current injection or primary current injection method, or the voltage method for the ratio test.
Thanks, Daniel. Our next question is going to be for Abel. Abel, is this the same way to test Rogowski coil CTs?
Oh, the Rogowski coil CT is a little bit different because the Rogowski coil operates on a differential principle. However, what that means is that for a current input, let's say on the primary of the coil, you're going to have a voltage on the secondary which represents the current that goes on the primary. The point here is that unlike in a regular inductive transformer where a current on the primary is transforming the current in the secondary by basically the turns ratio, if we neglect or do not consider the losses. In the case of the Rogowski, now you have a relationship between the current going on the primary and a voltage on the secondary. If you account for that, you need to perform on the Rogowski tests like ratio, polarity, and phase deviation, much like you would do on a regular inductive transformer. However, on the Rogowski, there's no saturation, so you wouldn't be performing any saturation tests. You would need to check insulation as you would do in any regular electrical equipment connected on the network, and there is no secondary winding resistance test because there is no winding on the secondary, right? So for a Rogowski, you would be checking ratio, polarity, and phase deviation. Okay, and you can do it using injecting a current on the primary and checking the voltage on the secondary, but they have a different principle of operation than inductive transformers. That's very important to understand when talking about this particular question. Okay.
All right. Daniel, can the insulation test cause remnants?
Thanks, Mike. And there's certainly a possibility. Remember, as a non-written rule, if I can say that, remember, anytime you are using any DC-based method for any measurement, there is a possibility that you can have some remnants in the core of the CT. So if Bonnie can help me show that slide where we describe the recommended sequence of measurements, where you notice that the two first measurements are insulation and winding resistance, both DC based, right? One is applying your DC voltage and the other is injecting a direct current winding resistance. And then you notice that the next phase in the test is demagnetization, right? To take care of that probable remnant flux in the core and to make sure that the subsequent measurements, all AC based, have no problem or are not affected by that remnant flux. So again, certainly a possibility. That's why it's recommended to run these two first and then go to demagnetization to then continue running your other tests.
Thank you, Daniel. Our next question is over to Volney. Volney, in the results obtained from the test performed, how is the FS that appears in our summary table calculated?
Okay, that is part of the IEC assessment. I guess this question is coming from a country that focus on the IEC assessment, and that honestly I don't remember right now exactly how it is done. I don't know if Abel can help me with that question. It's funny, this being the best panelists that I've had, they have not left any question and they just gave me the question that I didn't have the answer. Abel, do you have an answer for that?
I'm sorry. Well, yeah, that's okay. So the FS, that's le facteur de sécurité, security factor in English. That's a parameter that is used on IEC for I believe, metering transformers, and it's the maximum voltage that can appear on the secondary of that transformer. And the way we measure it is we basically extrapolate on the excitation curve. Okay, we extrapolate. Remember that the excitation curve has two sides. It has the linear part that I would say the operation point where you want the CT to operate with low excitation current and high or relatively high voltage, and then you have the other linear part too, but the one that's beyond the knee point. And in that other part, you have that for small changes in voltage, you have huge changes in the excitation current. Well, what the security factor tells you is for a particular overload, I don't know, 10 times, 20 times, 5 times of the nominal current of the CT on the secondary, what is the cutoff point that you want on the error, right? And the error on the CT, as Volney showed over there, is the excitation current. So the way it's calculated is we find the point at which the excitation current meets that criteria, and we find the voltage to which that, and we do it on the curve by simply intersecting the point in which we find that maximum error, and we bring it up to intersect the curve, and then we find the voltage, and then we compare that versus the value that was used in the nameplate of the transformer, because that is a parameter that is asked on the nameplate of the transformer. Okay, I'm sorry about that one.
Oh, the funny thing is I had it in the slides, but I removed it.
Oh,
Just in
okay.
the interest of
It's
time.
all right.
Okay.
It's
Okay.
All right, good deal. While we have you, Abel, the next question is also going to be for you. That is, what is the difference between ANSI 30 and ANSI 45? And how do we know if it's okay or not?
All right. Well, ANSI 30 and ANSI 45 are nothing but, let's say, it's two, let's say, different. Actually, it's the same way. We just use a different number of determining. Yeah, I see that Volney is painting there. Thank you, Volney. The knee point of current transformers. The thing is that the number indicates the angle or of the slope of the straight line from the origin, the coordinate origin, at which a tangent line can be drawn to the excitation characteristic. So ANSI 45, you would take a line that has a 45-degree angle, and you would have it touch the excitation curve in just one point. That's the definition of tangent, and that would be your knee point. For ANSI 30, that means using a line at 30 degrees and touching the curve. And the difference is that the 45 is used for CTs with non-gapped cores, and the 30 is used for CTs with gapped cores. And how do we know if it's right? Well, we need to know our CT. We need to know what type of CT we are testing. We need to have from the manufacturer the proper excitation curve, and we also need to know if the CT has a gap in the core or not. Typically, CTs with gaps in their cores are CTs where we want to have a higher knee point, right? And therefore, they have their magnetic characteristics are a little bit skewed or different than the CTs with non-gapped or continuous cores. Yeah, only is drawing two different. Now, to talk a little bit more about the excitation point, the saturation point or the knee point, IEC defines it a little bit different. IEC defines the point for which a 10% increase in the voltage produces a 50% increase in the excitation current. And actually, one way of mathematically defining that point, and they use it, is to draw a line to continue both, let's say, linear parts, and where they intersect, then you would draw a line perpendicular to the characteristic. I don't know, Volney, if you can draw that on a different, yeah, exactly. You continue that one, and then where they intersect, you would draw, well, yeah, okay, yeah, that would be your, actually, if they intersect outside of the characteristic, what you would do is you would bring a straight line across perpendicular to the characteristic, and that would be the definition by IEC of the knee point. Okay, thanks, Volney.
Thank you, Bill.
All right, moving on. Our next question's for Daniel. Daniel, if we change the order presented in the test by insulation, transformation ratio, excitation current, winding resistance, and finally demagnetization, what would be the difference between the two forms?
Thanks, Mike. And this is very specific to our instrument, our software, which is PowerDB, right? And customer is mentioning the form, which is what you see or in the results page, which is pretty much ready to print or share as a PDF. So if I go back to the same slide that we used for my previous question, where we have the sequence, this is actually the sequence the instrument will use if you use the automated button to run every single measurement. And if you do it manually, which of course you can, there is no change in the form. The software will just fill every section as you perform it. And there is no issues with that. The only thing is that in the sequence that here a customer mentioned in the question is that remember, right, what I talked about coincidentally in my previous question, you want to run a demagnetization in between or after those DC measurements, just to make sure that that probable remnant flux in the core does not affect the subsequent test. So if you do manually, if you select your sequence manually, no issues, just make sure you run a DMAG after any DC measurement.
All right, thanks, Daniel. Next over to Abel. Abel, is CCVT and CVT the same?
Well, the short answer is that for the purposes of this presentation, yes, they are. For the purposes of the fact that you have to do the measurements and whatnot, and what are they used for in the system from protection and measurement perspectives, yes, they are. However, there's a slight difference between CCVT and CVT in that CCVT is typically defined like that for it's a CVT, which can be used or is also used to couple with power line carrier communications in power systems. So, but there's a slight difference between them, but they're typically the terms are typically used interchangeably. So when you hear someone talking about one thing, sometimes they mean the other, but that doesn't really affect unless you really want to get into the down and dirty of a few of the things that could affect the difference right there.
Thanks, Abel.
Okay.
Over to Daniel. Daniel, in regards to knee point, what is the acceptable value of the result according to analysis?
Thank you, Mike. Well, great question. The analysis, right, the criteria to analyze these results a little bit different than the other aspects of these measurements we do for instrument transformers. We do not have a hard or hard limit or number that we're looking at, exactly a number depending on the type of CT. This has to do more with the application of that particular instrument transformer. Where do you have installed? What is the purpose of that instrument transformer? Again, there is no exact number or limit in terms of number of percentage that you're looking at. Once you get your knee points from your measurements, you want to make sure you are operating within the linear performance of that CT. If you can help me show a saturation curve, what we're looking at again is to make sure that whatever our operation conditions are, we are within the linearity of that instrument transformer. Of course, to make sure that whatever we are getting on the secondary, it's a proportional representation of our primary value.
All right, good deal. Our next question is going over to Abel. Abel, what can cause augmentation of the excitation current?
Okay, well that's a good question, because yeah, we typically do the excitation curve and then we look at it if it looks the same or similar, but then we rarely think about the causes of an increase of excitation current or a change in the characteristic, right? The first thing that can cause an increase in the excitation current is, and I know it's going to sound too general, a change in the magnetic circuit of the transformer. Right now, why does the magnetic circuit of the transformer change? It could be a change in the iron itself. Let's say there was a fault in the system. The fault drove the CT to saturation, and when the CT came back out, given that the voltage applied to the secondary of the CT during normal operation is so low, because at nominal current you will be talking about only a few volts applied to the secondary of the CT, then there will be some amount of remnant flux in the transformer, and that can increase just by not cleaning up the effects of the fault, can increase the excitation current on the transformer. Also, sometimes you have damaged windings. You have issues with shorts in between windings, that sometimes those are only detected when you drive the secondary of the CT to a high enough voltage to cause those shorts to show up. And that's one of the reasons why, even though it's done, a lot of times testing the CT with just a very low voltage to obtain the saturation curve, it is not something that is really recommended. A lot of utilities and users, they rather drive the CT to its maximum voltage, at least until the accuracy limiting factor voltage of the CT. For example, a C800, the people like to drive it at least to those 800 volts or something like that to verify that there's no problem in the insulation between turns of the CT. Other things have been mentioned here. For example, you do a winding resistance test on the CT and you don't perform a proper demagnetization, or sometimes you do perform the demagnetization, but the CT simply let's say some CTs, they have too much core, and then the demagnetization doesn't work as intended, and then you will have problems with the increase in the excitation current. So I mean, there are many different factors that can increase the excitation current. I just not mentioned a few of them. Okay.
Thanks, Abel. So it looks like that's all the time we have for our Q&A session today. I apologize if we didn't get to your question today, but we will be working to follow up with you offline. As a reminder, a copy of this presentation, certificate of attendance, and a link to the video recording of the webinar will be emailed to everyone in about 2 business days. I'd like to thank you all for attending, and if you could, please remember, answer our survey. That survey will include a field for you to request a quote or a demo if you're interested. But once more, I'd like to thank you all for attending, and I hope you all have a great weekend.
Thank you, Michael. Thank you to everybody. Bye-bye.